The kernel trick is a general method in machine learning that allows simple models to be augmented to give sophisticated results with relatively little effort. The key idea is that the model gets access to a complex augmentation or transformation of the data without actually computing this transformation explicitly. We discuss in this video how this is done.
In the case of support vector machines, the situation that we are looking at, or that we have looked at so far in this chapter, is this one where you have a data set and you are quite lucky in the sense that you can separate it with a linear function, with a hyperplane. And even though you might have some errors, like this blue dot being on the wrong side of the separator, still you do a pretty good job in terms of separating them with a simple, elegant, linear function, this hyperplane that we discussed throughout this chapter on support vector machines. However, in practice, you might also have examples that really don't seem to be well suited for the idea of linear functions. And for example, we have this one where we have a number of blue dots in here, but the number of red dots seem to be in two different regions of the plane. And so it would be much better if we could somehow think about separators that would take this into account. It would separate on one hand this part where you seem to have some red dots, and then it would separate this part where you have red dots, and it would leave the rest of the plane for the blue points. And then here is another example. You could also maybe have a situation like this where you seem to have red dots on this side and also red dots on this side, and you have here in the middle an area where you see quite a lot of blue dots. And so it would be quite useful to have a classifier which can take such a separator function that delimits this part of the plane for the red dots, and then also it separates this part for the red dots, and it leaves this one in the middle for the blue points. And then here is another example where you do have them separated in two parts of the plane, but a simple linear function doesn't seem to do a good job, but you would maybe rather prefer to have some sort of curved separator like this one. And this whole idea goes to suggest that maybe support vector machines, in the way that we describe them in this chapter, being linear functions in terms of the features of your data set, maybe sometimes in some cases they are not strong enough. And the same argument we had also when we discussed about linear regression. Sometimes there is only so much you can do with linear models, and you would like to have some sort of non-linear learning simply because your data seems to be non-linear. And the kernel trick that many people talk about, it's an extremely powerful technique, is really this idea that you would use a simple linear classifier to solve a non-linear problem. And that's what I want to just open the door to and give you some details about how this could be done, so that in practice you can really address situations like these ones that we have seen in these illustrations.
Recall that the so-called dual support vector machine problem was formulated in the following way. We had our dual Lagrangian, and this was of the form sum by t, where t was spanning the entire data set, by alpha t were the Lagrangian multipliers, minus 1 over 2, sum by t and sum by s, both spanning the data points. And then we had alpha t times alpha s. Then we had rt and rs, those being the labels of our data points. And then we had the data points themselves, the data point xt transposed times xs. And the problem was, the objective was to maximize this dual Lagrangian subject to all these Lagrangian multipliers alpha t collected in this vector alpha, and this was subject to and there were two constraints. On one hand, we had that the sum by t of alpha t rt should be equal to 0, and the other constraint was that all these alpha t should be between 0 and c, where c was a constant. And you can see now that the only place where we have our data points in this Lagrangian is right here. And so we have this inner product between these data points, and the inner product is a sort of a distance, or if you like, a sort of a similarity between these data points. And so our idea is that we would like to enrich our feature set and add extra features that are combinations of some sort of the original ones, so that in this way we get a more sophisticated separation between our data points, not just the linear one that's typically offered by the standard support vector machines. So we are looking for a mapping phi defined on r to power d. D was the dimension of our data set, taking value to into r to power k, where k is larger than d. And so the idea is that you go from d features to much more features than that. And the new data set that we are working with, so our new data set is going to be the set phi of xt for all xt in x. So if we have such a mapping, then we are going to go through the same derivations that we did for the support vector machines, and we are going to get the formulation of the dual support vector machine problem in this new data set. And what we are going to get is the following. We will get our new dual Lagrangian is going to be of exactly the same form as before. We will have a sum by t of these Lagrangian multipliers, and then minus 1 over 2, sum by t, sum by s, and then it's alpha t, alpha s, and then rt and rs. All of these things remain unchanged. The only thing that gets changed is that instead of the data points xt and xs, now we are working with phi of xt, and we have this transposed times phi of xs. And so the objective is, in this new data space, the objective is very similar as before. We want to maximize this Lagrangian by alpha, subject to sum by t of alpha t rt equals to 0, and alpha t are between 0 and c. So what we see here is that we are dealing with this inner product between phi of xt and phi of xs. Now what you have to realize is that this inner product, the result of this inner product is going to be a scalar. So effectively what we seem to be doing in this formulation of the problem is that we are going to expand our data set from d dimensions to k dimensions. K can be quite much larger than d, and each data point has to get its new extra features computed. And so we have to choose this phi. We have to transform the entire data set from d dimensions to k dimensions, only to have it somehow collapsing down to just one single dimension, because we are using this inner product. And so the main question we have in here is whether this effort could be avoided somehow, and whether there is any more elegant way of avoiding going from d dimensions to much more and then collapsing back into one. And that's what leads us to the kernel trick. The main question that we are asking in this kernel trick is whether we could somehow define a function k from r to power d times r to power d into r to power k times r to power k in such a way that when you have this transformation phi of xt transposed times phi of xs, which was the inner product that we had in the new expanded version of the support vector machine problem, somehow this would be equal to k of xt and xs. Now, if we could, then we would have all the advantages we were seeking in a nonlinear model, but we would deal the entire time only with the original data set, not with this large expansion of it that we have to go through if we are going through the mapping phi. And so for such a kernel function, the kernel support vector machine becomes the following. We have the Lagrangian being, just like before, sum by t of these Lagrangian multipliers alpha t minus 1 over 2, and then we have a sum by t, a sum by s, alpha t, alpha s, rt, rs, and then all of a sudden, instead of the inner product, if there was such a kernel mapping, here we would have just k of xt and xs. And you see this whole Lagrangian now all of a sudden skips the mapping phi, meaning that we don't have to really calculate this mapping phi. It all goes through this kernel function k. And the point is that this is a general idea. It's not just in support vector machines. It's a general idea to get a more sophisticated model through a kernel. As long as the problem somehow can be formulated in terms of an inner product, then the kernel trick can be applied to that formulation of the problem, and we get the so-called kernelized version of the problem. And this is where the name kernel machines come from. And in a kernel machine, the only thing that we need is the matrix of values. So we would need these entries, KTS, which is exactly the calculation of the mapping applied to data point xt and ss. So we have all of these data points, and if we can calculate this matrix K, then we have access to everything that we need in order to solve the kernelized version of the problem. As a matter of fact, when we are using the kernel trick, quite often storing the dataset is even skipped, and it's replaced with storing this so-called gram matrix. This is the gram matrix holding just these values of our data points through the kernel function that we are choosing. And there are quite many kernel functions that are useful in different machine learning problems, and we are going to discuss those in a separate video. And also we will discuss in another later video how to build your own customized application specific kernels based on already known kernels.